welcome to the last big unit of calculus. This is going to be all about integrals. So, differentiation is the process of finding derivatives. So what we're going to do with integrals is actually the reverse. So we're going to call it anti-differentiation. Keep in mind, we can use different words for that. So an antiderivative is kind of what we're looking for. We're going to be given the answer basically, and we need to figure out what did that start out as, okay? So it's the inverse process. So for example, if we had y equals x cubed, we know that the derivative is 3x squared. So what we can say is that the antiderivative of 3x squared is x cubed. Okay, so and that's what we're going to be given the entire quarter. So that's how you have to think of it is, oh, this was the derivative. So what was the original function? All right. So it's super, super important to realize there is a specific distinction. So we're going to call it an antiderivative because it's not the antiderivative since we have a few reasons. So what if we had, look at the table over to the right, all of these functions as the original, okay? Well, if I had all of these functions, all of their derivatives would be 3x squared. But these are all different original functions. So that's why we're kind of getting that idea. Are you following me so far? So when we do that, when we have 3x squared as the derivative, we say the original is x cubed plus some unknown constant. We won't be able to know without more information what that constant is. And so it's super important to attach that plus c after every single antiderivative. Now, that is something you're going to forget. Hopefully you won't in about a week. But on a free response question, if you don't put the plus C, then you can't get points after a certain value. So if the question was worth, let's say, 5 points on one part of it, if you don't put the plus C, you might lose the last 3 points. They might give you the first 2 points, but you won't be able to get anything after that. So it is actually super important that you remember the plus C. Okay? All right. I have a little bit more here for you to read. I won't read all of that to you, but we can call it an antiderivative, but even that, honestly, is just so long for mathematicians to say. We call that integration instead. So like derivatives, differentiation mean the same thing. Integration is the same thing as an integral, all right? And so that's what we're finding. If we're given the derivative, the original function, is called the integral. That's the process. So because we have some notation here, indefinite integration is what our first topic is going to be. Okay, so we're never going to say this word antiderivative again. All right, so let's talk about some of the symbology. So this little symbol right here, that is called the integral sign. All right, and so what you're going to notice is when we're given problems now, it's going to look like this. These are what the problems look like. Now, there's one slight difference, and I don't know if you can even tell, as what do we have? So the integral, that means to find the original function. Why does that always look so different? Hold on. Origin. Oh, function. So I have to say it to myself. But there's this little dx, and it says, ooh, what is dx? Now, we hit upon this last quarter, but honestly, probably about for 5 seconds, and then it just went away when we did implicit derivatives. So remember, if I had an original function, like x cubed, let's say that's y, we could write it as y prime, our derivative, is 3x squared times the derivative of x with respect to x. So we had dx over dx. Dx over dx is 1, so we never saw this. But now that we have, we're going to be reversing the process, we have that dx there. And so all that indicates is that this is a derivative. So it indicates two things. One, that it is a derivative, indicates it's a derivative, but it also indicates what the variable is. X is the variable, okay? So now it's like, well, what do we do with that? Honestly, you really don't do anything with it. It's just for you to understand what's being given to you, what things mean, so it can help you. Because eventually, like, our variables change, things like that. All right. So here's a few examples. We can do trig, we can do e, we can do lots of different functions. But these formulas, I wouldn't say you necessarily have to memorize them, but I'm going to kind of talk about what they mean because these are the ideas. And they're the same rules, basically, that we had for derivatives. So if I integrate 0, that means I had to start out with a number because the derivative of a number is 0, okay? If I have a number, remember k is a number because x is the variable. So if I started out with a number like 5, well, what did that have to start out with? Well, it had to have a power of x. So this would be 5x plus c. If we have an integral that has a number being multiplied in front, it's the same thing as a derivative. You can kind of factor out that constant, integrate your function, and then multiply it back together. We can add or subtract different functions and do them separately. That's what this means. And then this is going to be the power rule for derivatives. This is the first rule that you're going to memorize. So when we had, let's look at our derivative. If we had x to a power, we brought the power down, and then we subtracted 1. So if we want to reverse that process, this is really the shortcut. Well, we need to add a power, and then instead of multiplying, we're going to divide by that new power. So like if we have x to the 6th, let's say, it means we would do add 1, so we get x to the 7th, and then we're going to divide by that. Now, you can write it as x to the 7th over 7th, or it's really like 1/7 x to the 7th plus c. And we're always just going to have, no matter how many times we do the adding or subtracting, it's always just one generic constant at the end. All right, so that's the first integral rule for you to memorize, is the integral power rule. So, just like with derivatives, you want to write things as single powers of x so you can utilize the power rule. Notice none of these are going to be quantities because that's going to be a different integral rule. So let's look at these 4. Remember, when you add or subtract, sometimes you'll see me write them with an integral symbol because it really means I'm integrating them separately. So that's a power and that's a power rule. So I'm going to add 1. And until you get used to this, you might write that for yourself to help you remember. So add 1, and then we divide by that same power. The minus stays, and then I'm going to add 1 and divide by it. And you get 1 plus c at the end. Notice when I integrate, that integral symbol goes away and the dx goes away. Okay, we don't keep that there. All right, since e is not to a power, e is just a number. This is like x to the 1st, because x is our variable. Okay, so we're going to go ahead and integrate these separately. So I'm going to keep that e as being multiplied. So I keep the e, and then I'm going to add a power. So x squared divided by 2. Now, this doesn't have a power of x. So you can think of that as like x to the 0. So if we add 1, I would get plus 1 over e stays, that's being multiplied. So x to the 1st, and if I divide by 1, it doesn't change anything. So I don't even write that. And that would be my integral. If I did this derivative, and you can always check yourself, I should get that. Okay. Now, we don't have a quotient rule yet for integrals, so I need to rewrite this. When you rewrite something, keep your integral to tell yourself that you have not done the integral yet. The 2 is going to stay, and I'm going to write this as x to the negative 3 minus 5, and then x to the negative 4, and then dx as a notation. So now we can go ahead and do these separately. So I'm going to keep the 2, and then I'm going to add 1. Especially when you have negative powers, I like to see that because these are really easy to get confused in your head until you get used to it. So if I add 1, I actually get -2, and then that's what I'm going to divide by. Don't worry about simplifying that yet. You want to get better with this. So -5 stays, and then I'm going to add 1. So x to the -3, and then that's what we'll divide by. And then we're done integrating, so I'm going to put the plus c. Now we can do the cleanup. So cleanup means to reduce the coefficients and change your negative powers, okay? So 2 divided by -2 is -1, and then this is going to come down as x positive squared. 2 negatives make a positive, so I get plus 5/3, and then I'll bring my x down, plus c. Okay, and then this would be as clean as you can get. Typically, the rule is you want it to be the same format. So if this started out as a fraction with positive exponents, then your answer should be the same. Okay. All right, example number 4. Once again, we're going to rewrite these as powers. So remember, it's x to the power over root as a rational function. So I get 2, 1/3 minus 4, and that's like a 1. So y to the 1 power over the 4th root, and that's dy. So notice we can change, y isn't our function. They're now saying that y is our variable. Okay, so that's kind of how the notation works. So we're going to leave the 2. If I add 1, all that really does is it adds the numerator and denominator together. Okay, so I get 4/3. And then instead of dividing by 4/3, remember dividing by a fraction, we're going to multiply by the reciprocal. So I like to multiply it in front. So the reciprocal would be 3/4. Because we are dividing by a fraction, it's just saving us that step. Minus 4y. If I add these together, I get 5/4. So multiply by the reciprocal, and then plus c. So it's really easy if you don't write this out to think like, oh, I bet the 4's are going to cancel. No, they don't. All right, so let's clean this up. So we would get 6/4, which is 3/2, y to the 4/3. And we don't typically, they might write it in the radical form, or you can leave it as the exponent. Minus 16/5, y to the 5/4, plus c. And typically I do put the fraction in front being multiplied. I don't put the y in the numerator. It is there, but that's how I write it. Be flexible. Okay, so all 4 of those utilize the integral power rule. Now, just like with derivatives sometimes, to take integrals, you have to be a little more clever than you probably ever did with derivatives. But we did do this way back when you first did the derivatives at the very beginning. Okay, there's a limited set of rules. You only know the power rule. Okay, so that's all you know right now. So we actually never get a product rule, and we never get a quotient rule for integrals. Okay, so there's actually less rules for integrals. So if we can't write it as the sum of expressions, then we might have to change it. So I've got 2 different examples of what we call the bag of tricks. And we did this bag of tricks for derivatives too. So remember when we were doing the derivative of this, what did we have to do? Well, we had to write it out. Now, eventually, we will actually be able to do this problem, but I wouldn't say it's going to be quicker. Okay, so this is not a bad strategy to learn. It's not like the process that we're going to learn how to do this in a few days is going to be faster. So I would probably do it this way too. So we're going to write out 2 of these. And then we're going to have to just multiply. So 2x times 2x minus 6x minus 6x plus 9, and then I would combine like terms. So 4x squared minus 12x plus 9. Notice I keep all of the symbols because I have not done my integral yet. That also tells you that you've not done your integral because sometimes it's really easy to forget. Okay, so we'll go ahead and do all of these separately since they're being added and subtracted. So I'm going to keep the 4 and I'm going to add 1 and divide by it. This has a power of 1, so we'll add 1 and divide by it. And then this doesn't have a power, so I'll add 1 and divide by it, plus c. So notice I don't do any of that cleaning up. And I think I've taught calculus for like 17 years, and I still do it this way. It's just too easy to make a silly error. And then simplify. Now, can you skip some steps? Sure, but try to be really clean with your notation, okay? The next problem, example 6. There's not going to be a faster way to do this problem in the future, so this will be your only strategy that you need to utilize. We did this with derivatives too. We don't have a quotient rule for integrals, but we didn't want to do that anyway. We tried to avoid that. So really, I want to think of this as splitting these up. So split up. And remember, the rule is you can only have one term in the denominator. If you have more than one term in the denominator, you're not going to be able to do this. So we get x squared over this. And yes, you can do this quicker, but I want to make it very clear what you're actually thinking of. So then I'm going to reduce. And then this turns into problem 3. So now we need to rewrite this. Notice I still have my integral. I have not even integrated yet. We're just getting this ready. The 3 stays. We'll bring this up. Okay. So now that everything's written as a power, now I would do the integral power rule. So I'm going to add 1 and divide by that. The 3 stays. Add 1 and then add 1. One constant at the end. So then we'll clean this up. So negative 1 over x minus 3 over 2x squared minus 1 over 3x cubed. Okay. Now, I don't know how some of you might be able to go from the red to the final black. I don't. I literally don't skip any steps. Okay. All right. The next thing is we're going to talk about kind of a term that we'll see later on at the end of this quarter. And so what it's saying is if we were given a derivative, like the derivative is 4x, we can integrate each side and then we get all of this work. So we integrate, we get that, and then we get this. Now, if we want to do that, that's fine. The original statement, which is the derivative, it's called a differential equation. And in college, there's actually a whole class called DiffEq, Differential Equations. Electricians have to take it. Math majors like me had to take it. So you learn a lot. So this is just a term, all right? So differential equation. That should make sense because it's a derivative. That's all that actually means. So in a differential equation, you're given a statement about the derivative, and your goal is to solve for the original. Because the constant of integration is c, we end up with a general solution. So all of these derivatives that we found, this is just called the general solution because it has that plus c, okay? It works for a whole family of answers. We don't know which one is the actual answer though, okay? So what's going to happen is we need some more information. So what we need is we need an original point. So if we're given an original point, which is called an initial condition because it's on the original function value, once we know that it's kind of like anchoring it, then we can actually find the constant value for our general derivative, general integral, and then we have a specific solution to the differential equation, okay? So then once we know that, they plugged in x is 0, y is 5, and we got that our constant value is 5, so then they went and they replaced the c. So this is called the specific solution, okay? It's a solution because we were looking for the original equation, and a specific because we don't have any generic variables anymore. So the directions are going to say this. It says solve the following differential equations with the given initial conditions. So it sounds super hard, but it's the same process we've been doing. It's just going to be more steps. So what we want to do is we want to integrate both sides, okay? So we're going to keep this for later. So if I integrate the derivative, I get the original function. See, I can do the left, and then we're going to do the right. Well, to integrate these, we're going to do the power rule. So I'm going to add 1, divide by it, add 1, so minus 2. So add 1, add a power of x, and we still have our plus c. Okay? So this is the general solution. Now, f of x, remember, that's a y value. So this is x, and this is y. So f of x is our y value, and we know our x value. I could clean this up. I'll kind of do it at the same time. There's not much to clean up. So if x is 3, I'm going to plug that in. So once I plug in x and I plug in y, the only thing that's left is actually solving for c. So that's what we want to do. So I get negative 1, 27 divided by 3, 9. The 9's cancel. That's just a coincidence. So we'll subtract 6. So c equals negative 7. So we're going to take that, and then we're going to plug that in. So our specific solution, and that's why I can use the f of x, is going to be x cubed over 3 minus x squared plus 2x, and then this is our c value. So that is our specific solution. We found the exact original equation that would meet that condition. There's no other answer that would work. Okay? All right, example 8. Notice I'm given the second derivative, a first derivative value, and an original value. So because I'm given more information, I actually can find the original. So let's start. If we integrate the second derivative, well, one step up is the first derivative. Okay, I integrated, so that integral symbol's gone. This is going to be a power rule, so I'm going to add 1, so I get 2, and then add 1, so x squared divided by 2 plus c. Now, I'm given an initial derivative value. So this is x, and this is y, but of the derivative. And so I have the derivative here. So the y value of the derivative is 0. I'm going to reduce that. My x value is negative 3. Please use parentheses. And I can find c. So I get 0 equals 9 plus c, subtract 9. And so the constant value, this is like my first constant. So I'm going to put a little 1 subscript for u. So I'm going to plug that in. So what we know is that f prime of x equals x squared and then minus 9. Okay? But I also know an original value. So I can integrate again. So if I integrate the first derivative, we get the original. And then a power rule. Add a power, divide by it. Add a power, divide by it. And then plus c. So now this is technically our second constant. So we know that this x value is negative 3, and the f of x or y value is 10. So 10 equals negative 3 cubed, 9 times negative 3, plus our second constant. Now, you don't have to write the little subscript 2. I don't. But I know mentally it is a different constant value. Okay, so we just always let a C be in general. So 10 equals, what's that? Negative 27 divided by 3 plus 27 plus C. 10 equals, what's that, 18? Subtract 18. All right, and so we're plugging that one in for our second. So our original function, which is our goal, is x cubed over 3 minus 9x, and then minus 8. This is our particular solution. Okay. All right, so I gave you a few rules to try. I do have a bonus there. And I didn't ask any of these questions, but you will see that later.